Okay, good evening, everybody. Welcome to another organic chemistry session. Okay, before we start the session, I do have some announcements. Next Tuesday, that is September 18, the first 1-hour exam. So I want to remind you of that. And because of that, on Monday, September 17 at 8 p.m., we will have an online review session. For that online review session, we will go over the first exam from the previous semesters. And by the way, I posted that exam already in Blackboard. How many of you have seen it? Okay. So you may want to take advantage of that and see how many of those problems you are able to do. So the session on Monday will be at 8 p.m. 8 p.m. on Monday. So go ahead and use the same link that we have been using for the rest of the semester. Yes.
Are you going to post the answers for that so we can check?
We are going to do it. We'll do it in the online. Okay. Also, do not forget that the OWL assignment for this week is the end of chapter questions for chapter 3, and that is due on Sunday. That is September 16th. Okay, so let us get this session started today because we do have a lot of material to cover. Do you want us to go over the quiz?
Yes.
Okay, good. Spencer, can you go ahead and read this question for us? Okay, what is the IUPAC name for the following compound? This is the compound they want you to give the name, and of course you have been given multiple choice. Okay, so you have to choose one of these names here that belong to this molecule. So what is the correct answer? D. How many people agree with D? Okay, D is correct. D is correct. Now, why do you say D is correct? Okay, the base name is, you have 7 carbon atoms in the base name, which is heptane, right? So that means this is out, and that also means this is out, right? If it's going to be heptane, so the choices will be between B and D. And then if you take a look at the numbering, of course, this is carbon 1, 2, 3, 4, 5, 6, and 7. And the substituents are in positions 2 and 5. And that is why the correct answer is D. Okay? Now, having said that, let us now take a look at the rest of these molecules here and see if you can name them or if you can give the structures for these molecules right here. I'll let you know now that 2 of these names here are wrong. I also want you to let me know which one of those two, which 2 of the names are wrong. So let us go through it. Can I erase this? Okay, good. Okay, so let us start with the first one. A, 2-ethyl-4-methyl-hexane. I said 2 of the names are wrong, so you need to let me know which one is wrong. Okay, so what would be the base name for this one here? Hexane. Okay, so let us draw this here. You say hexane is the base name. That's 2, 3, 4, 5, and 6. And then in position 2, you have what group? Ethyl, right? Okay, so if we say we number the positions here, 1, 2, 3, 4, 5, and 6. Okay, so we say position 2. We have ethyl group in 2. So we remove one hydrogen. Keep in mind, you cannot violate the valence rule and the octet rule. All of those things that we told you in chapters 1 and 2. So here, we need to replace the hydrogen with ethyl. So we take out one hydrogen, and we place the ethyl there. Ethyl is in position 2. Then in position 4, you have methyl. Okay, so right here. So we remove one hydrogen, replace with a methyl group. Okay, so that is the structure they have given us. Is that the correct name for that structure? What is the name? What is the correct name? What do you think the correct name should be? What is the longest carbon chain? Okay, where do you start counting? Okay, you want to start counting from where? Here? Okay, say carbon 1, 2, 3, 4, 5, 6, and 7. Okay, so the branches will be in position 3 and 5. Is that right? Okay, so the name will be 3, 5. Don't forget between the numbers you put a comma. Then between number and name you put an hyphen. Dimethyl. Very good. Alkane. Very good. So therefore, this name is wrong, right? This is one of the names that are wrong. So this is wrong. Okay, very good. About B. About B. What is the longest carbon chain? The base name for B? Alkane. Okay, so let me start with 7, right? Two, 3, 4, 5, 6, 7. Okay, so that is the base name. Yes.
I have a question about the first one. Why is it dimethyl when one is an ethyl and one is a methyl?
Okay. If you, the longest carbon, this is the base name. Just a minute. That is the base name. You see that? And you have a branch. The ethyl group is in 5 position. That's the branch. And the another methyl group, I'm sorry, the methyl group is in 5 position. And another methyl group is in the 3 position. So because you have 2 methyl groups, that is why we call it di.
But we don't count the ethyl as a branch.
But the ethyl is part of the chain. You see? Don't get confused because the way we wrote the structure. But you have to look for the longest continuous carbon chain in the molecule. Okay. So you have 7 here. So therefore, we have 2 for dimethyl. So if we say this is carbon number 1, right? So therefore, there must be the 2 position methyl group. And if we say this is 1, 2, 3, therefore this must be carbon number 4. So we take this out. We place another methyl group. Okay. And so therefore that becomes 2,4-dimethyl-heptane. Okay, is the name they gave us, is it correct? It's correct, right? Okay. Very good. So that is correct. So everybody clear with that? I'm going to erase this. Can I erase this? Okay. Okay, so let us do the C. C. Okay, 2-methyl-4-ethyl-hexane. By the way, there should be no hyphen between the ethyl and the hexane. That's an error. Okay. What? Okay, I was going to get very good. It's also wrong because it's alphabetical order. I told you 2 of them were wrong, so this is one that was wrong, and this is also wrong because the name is not in alphabetical order. So let us see whether the structure, the way that is the correct name in the first place, even without the alphabetical order. Let us see. Okay, the base name is what? Hexane. So take your time to write the base name. Okay, that's hexane. And then in 2 positions, you have methyl group, right? Let us say this is position 1, and therefore this is position 2. There's a methyl here. In the 4th position, you have, this is 4th position, you have an ethyl. So far, so good. Okay? So what would be the name? Is this name correct? What would be the correct name? This is position number 1. And this is position number 6. What would be the correct name? 4-ethyl. Very good. Because we have to name in alphabetical order. 4-ethyl. 2-methyl hexane. Okay, so I see you guys have no problem with nomenclature. Very good. Yes. Oh no, it doesn't. It doesn't matter. Okay, will you start the number from here? In other words, give this number 1. Okay, let's try that. Let's see what happens. Supposing we call this number 1. 1, 2, 3, 4. This is 5 and 6, right? So the branches will be in position 3 and 5. If you add 3 and 5, 3 plus 5, that's 8. Okay, on the other hand, if we number the way we had it before, this was position number 2, right? And this was position number 4. So 2 plus 4 is 6. So you look for the lowest combination of number. So that is why we pick this one here. Okay. Okay, so we finish with question number 1. Okay. Let us go to 2. Okay, Brianna, go ahead and read this for us. Okay. Okay, very good. So there is a lot to do in this particular problem. But it's thing you need to be aware of one thing I have here. I have two of the molecules must have methyl substituents. You know, this is a plural substituents. Okay, in other words, I expect to have more than 2 methyl groups in each one of those molecules. Okay, but if you just give me one methyl group as a substituent, I will give you some credit. Well, I understand. I will give you credit. Next time I will make it better. I will make it more clear so that you know exactly what. So that you know exactly what I want. Okay. Yeah, I know exactly. Okay. If you just have one methyl, then I will let you go. But I go with it. Okay. And the third compound must have an ethyl branch or substituent. Okay. So we all agree on that, right? Okay. And we also know that the molecular formula is CH18, okay, for all of them, all of those 3 compounds. Okay, so let us start. This is what I have in mind. Okay. Okay, I want to put 2 methyl group as a substituent. What that means is the longest carbon chain must be what? 6. Okay? So therefore, I start with this. But like I say, if you decide to use only one methyl substituent, I will give you your full credit. Okay, so that is the base name. Then you could actually come up with all kinds of structures for this. There's no particular answers to this, as long as you obey all of the valence rule and the octet rule. So my answer may not be the same as yours. So I place one methyl here. And then I decide to place another methyl here. That is a possibility. So what would be the name of that compound? To do what? Yes. The question is, can you use a skeletal structure? Yes, you could use skeletal structure. Yes. You have a question? Yes. Oh, yes. Okay, 3, go ahead. 3, 4, dimethyl, hexane. Okay, do you all agree? Yes. Okay, that is correct. So that is one possibility. Then I would say another possibility would be this. The longest carbon chain is 6. The base name is 6. 1, 2, 3, 4, 5, 6. The question is why is it an hexane? Okay. Okay, so I'll do another one. Yeah. Yes, we could. Yeah. Okay, let me do this. Then I'll come to that. Okay. Folks, let's have some quiet. Okay, so that is the base name. Then I will keep in mind that it has to be a different compound from this. The only way you know that the 2 compounds are different if you give them different names. Okay? So I come here, I take this out. The methyl is here. And then I take this out. Take another methyl here. Okay, can you give the name for that compound? What would be the name? 2,3-dimethyl. Very good. Hexane. Okay, so those would be the two possibilities in terms of those two compounds that have methyl substituents. But you said that we should do one with one methyl group. Okay. Okay, let us do one with one methyl group. In that case, what would be the longest chain? It would be 7, right? Okay. In that case, you could have the methyl any part of the chain. Okay, so we have this. So that is the base name. Then I have to simply just take replace any one of these hydrogen with a methyl. And what would be the name? Three-methyl heptane, right? Mm-hmm. What is the longest chain? That's what we... Okay. Okay, so anyway, those are the possibilities. Now, about the one that says you must have an ethyl group, what would that look like? What would be, since the ethyl group is 2 carbon, so what would be the longest carbon chain? 6, okay? So therefore, we will have this. And then I remove one of this hydrogen. You could remove this hydrogen here. I replace with an ethyl. And what would be the name of this compound? 3-ethyl hexane. Okay, very good. Okay, so far so good. Yes.
Is it okay if we did C2H5? Or does it have to be C2H2, C3H? I mean, sorry.
Okay, okay, let me tell you now. Yes. I do not want to encourage that. Do not do that. I want you to do the CA2, CA3, yes. Okay. Yes. Yeah, there's some other possibilities, yes. Okay, as long as, the longest carbon chain will be 6. Okay. Okay, now, so now I think you guys are very comfortable with at least some aspect of nomenclature, so I'm glad that that is the case. Now, the reason I gave you this problem here is to introduce to you another concept. And that concept is what we call constitutional isomers. Take this out. We say constitutional isomers. Constitutional isomers are what? Yeah, you could use a skeletal structure. Well, let me finish with constitutional isomer. I will get to that. Okay. Constitutional isomers are different compounds that have the same molecular formula but different attachments of the atoms. Let me write it down for you. different compounds having the same molecular formula but different attachment or different arrangement of the atoms, but different attachments or, if you like, or arrangements of the atoms. Now, this is a very important concept indeed. We are going to be dealing with a lot of isomers as we go along in organic chemistry. This type of molecules we call constitutional isomers. In other words, let me just label. Let us say this is compound A, right? Say this is compound B, right here. And this is compound C. So what we are saying here is that compound A, B, and C are constitutional isomers. Because if you look at what we have here, they have the same molecular formula, but the attachment of the atoms are different. Okay, let me give you further example. Supposing I have this molecule here, C5, H10, and I ask you, in the future, I will ask you to give me, to write all of the constitutional isomers. You know, the question I gave you, question number 2, the reason I did not use the word isomers, because we have not done it in class yet. In the future, I will simply say, give me all of the possible constitutional isomers. So let us write all of the possible constitutional isomers for this model, for this formula here. C5H10. Just try it. I'll give you 1 second to do that. How many do you think you can get? How many? How many is a lot? Because we want to start with the straight chain, right? The carbon attached to each other, carbon, 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 right? Okay, let's do that. Let me just. That is one possibility, right? The formula is C5, it has 5 carbon and 10 hydrogen. Is that correct? What is it? Oh, sorry about that. Sorry about that. I do want to make this 12 hydrogen. You guys should have caught that. I was trying to give you an alkane. That is not the formula of an alkane. Okay, thank you. Okay, so the formula is C5H12. C5H12. So this is a possibility, right? What is another possibility? Is that another possibility? Yes, it's the same formula. But look at the attachment, they are different. This one is completely, it's a straight chain. All the carbons are attached in a straight chain, and this is a branch alkane. Okay, what other possibility do we have? Anybody can think of? What is it? The metal will be on the third carbon. This here. This here. It's already there. Yes. It will be, yes, it will be right here. Which one? Replace the hydrogen with a CH3. Very good. Okay. That is another possibility. Each one of these compounds here, the relationship between them is what we refer to, they are constitutional isomers. These are all constitutional isomers. So now you guys have, at least you get the idea, when we say constitutional isomers, simply means that you have different molecules or different compounds having the same molecular formula, but different attachment of the atoms. Okay. So these are all constitutional isomers. I also want to use this to introduce two other concepts. Okay, can I erase this? Yes. And that is the different types of carbon and different types of hydrogen in organic compounds. Of carbon and hydrogen in organic compounds we have what we call hydrogens. Everybody follow that? This is hydrogens. We have what we call primary hydrogens or primary carbons. The primary carbons, sometimes we do designate this as, sometimes we use this designation 1 degree, okay, for primary. The primary carbons are those carbons that are only attached to one other carbon atoms. Okay? Only attached, attached to only one carbon atom. In other words, if you look at this molecule here, this carbon here, we refer to this carbon as a primary carbon. Because this carbon is only attached to this carbon, only one other carbon, that's all. However, this carbon here, what kind of carbon is this? This is also a primary carbon. Now, the hydrogen that is attached to a primary carbon is called a primary hydrogen. You follow that? The hydrogen that is attached to a primary carbon is called a primary hydrogen. So what type of carbon is this? Primary. What type of carbon is this? Primary. Very good. So now what we are doing now is teaching you some of the organic chemistry language. After a while, we're going to be talking organic. Okay, what kind of carbon is this? Primary. Okay. Now, for the secondary carbon, then we have what we call the secondary carbon. Which we designate as the secondary carbon is only attached to 2 other carbon atoms. Say attach to 2 other carbon atoms. So therefore, if we look at this molecule here, this here, what type of carbon is this? That would be a secondary carbon. And the hydrogen that is attached to a secondary carbon is called a secondary hydrogen. Okay. What type of carbon is this? Secondary. Okay. The same thing here, secondary. Same thing here, secondary. Okay, so far so good. Can I erase this? Then we have a third type of carbon that we call the tertiary carbon. And we designate that as this here, tertiary carbon. For the tertiary carbon, what do you think the tertiary carbon is? Attached to 3 other carbon atoms. Very good. Attached to 3 other carbon atoms. Okay, so in this molecule here, this is the tertiary carbon right here, right? That is your tertiary carbon right here. Do we have any tertiary carbon in all of these molecules here? No. That's it. That's the only tertiary carbon we show right here. And the hydrogen that is attached to a tertiary carbon is called what? Tertiary hydrogen. Okay. What time do we have? Oh, plenty of time. Plenty of time. So therefore, we have so far we've given you 3 types of carbon: primary, secondary, tertiary. Now we have a 4th type of carbon. We call that the quaternary carbon. Now, for the quaternary carbon, that carbon is attached to 4 other carbon atoms. Four other carbon Okay, so where would be the quaternary carbon in all of these structures here? This one here. So we only have here 1 quaternary carbon. So this is your quaternary carbon, also designated as that. So essentially, therefore, we have 4 types of carbon In organic chemistry, we have the primary carbon, secondary carbon, tertiary carbon, and quaternary carbon. And for the quaternary carbon, does it have hydrogen attached to it? No, it does not. Okay, so having done that, let us do the third question in the quiz. You want us to do the third question in the quiz? Okay, let us see here. Spencer? I called you before, right? Let me see. Who did that? Asim? Can you read this for us?
Draw the structure of 4-chloromethyl, 2-methyl alkane.
Very good. Okay, what they want us to do here is to draw the structure of 4-chloro, 4-chloromethyl, 2-methyl alkane. Now, before we do that, let me let you know that as we go along, even though we are dealing with the chemistry of alkanes, we are also going to be using some other substituents. For example, if we have fluorine, if we want to use fluorine as a substituent, we refer to it as fluoro. If we have chlorine, we want to use it as a substituent, we call it chloro. We have bromine as a substituent, we call it bromo. We have iodine as a substituent. These are some of the more common substituents called iodo. In addition to the alkyl fragment that we gave you earlier. Now, if you also remember, we gave you the alkyl groups. And we told you that the alkyl groups are fragments of the alkane molecule in which you simply remove one hydrogen from the corresponding alkane. For example, if I have this, if I want to make an alkyl group from this part of the molecule, I could simply remove this here. I attach something to here. So now this becomes an alkyl group. That becomes your alkyl group. And this particular case, this is a butyl group because it comes from butane, right? You remember what we told you last time we met? Butyl group. Now the position of attachment in all the alkyl groups will be position number 1. In other words, this alkyl group, this is position number 1 because that is where it is attached to whatever we want to attach the group to. Okay, 2, 3, and 4. Now supposing I now have, I take one of these hydrogen out and now place a bromine here. What do you think I will call that fragment? 3-bromo-butyl, exactly. So it becomes 3-bromo-butyl, one word, 3-bromo-butyl. Now, this is where I want to go with this. Now, supposing now this, yes. Because this is position number 1. The position where the fragment is attached to whatever group is always going to be position number 1. Okay? Now, this is what we want to do with this. Supposing, therefore, by the way, because this is the first time I will be explaining this. This question here will only be worth 1 point. Okay, out of the 12. Okay. It will be worth 1 point, okay? 1 point. Okay. Okay, now, supposing I have this. That's 3, 4, 5, 6, 7, 8, 9, 10, 11. What would be the name of that compound? Dodecane. Very good, very good. Supposing now I attach this fragment to dodecane, right? Where do I want to attach it? Let's say I attach it to 1, 2, 3, 4, 5, 6. Let's say I attach to here, 6 carbon. Take this out, right? I'll now place this fragment CH2, CH with the bromine in there, and CH3. What do you think I will call that compound? Now, what we have now, that substituent here is now what we call a complex substituent. A complex substituent. So whenever you have a complex substituent, you have to use parentheses to show that, to indicate the position. When you indicate the position, you must to close the complex substituent in a parenthesis. Okay, so in this case, the name of this compound will become what? Any guess? 6. Okay, very good. So now we're going to say 6. Then I will say paren, because this is a complex substituent. Then I will then name the branch as give it the name of the branch itself. What is the name of this substituent? 3-bromobutyl. Now be 3-bromobutyl. Then I close the paren, and then I go ahead and give the parent name, right? In this case, dodecane. Okay. So now I've been giving you that. Let us now give the name of this molecule here. Yes. This is bromine. Which one? This is bromine right here. Let me write it so that you can see it better. Let me erase. That is the bromine right here. Let me use a different pen. Bromine is attached to, oh, wait a minute, let me. Okay. The bromine is attached to the 3 position of this fragment, this alkyl group, because this is position number 1. The position where the alkyl group is attached to the parent name or the base name, that will always be position number 1. Okay? And that is why we say this is 3-bromo, because if this is 1, that's 2, that's 3. Okay. Now let us go ahead and name this compound here. Let us give the structure of this compound. Anybody now know the structure here? 4-chloromethyl, 2-methyl undecane. What is this fragment here? Chloromethyl. What will it look like? Chloromethyl. Exactly. So it will simply be, because this is your methyl right here, right? That's your methyl group. Okay, and therefore you remove 1 methyl. So that's your chloromethyl. Okay, so therefore the structure will be this. How many do I have so far? 11? No. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One more. Okay, so now, where would the chloromethyl go? 4 position, exactly. So I take out 1 hydrogen. Okay. So sometimes you may have a complex substituent. You have to put that substituent in parentheses. Okay. So I think by now everybody is comfortable with nomenclature. So I think we can move on to the next. Oh, I'm sorry. 2-methyl. Yes. Sorry about that. We have 2-methyl. So the 2-methyl, we have methyl in the 2 position, and that would complete the name. Yes. Okay. Okay, so at this point, I want to go to a slightly different topic. You guys are having so much fun there. That way, Dwayne and let me put the camera on you. Okay. Okay, so now what I want to do now. Okay, what we want to do now is now begin to introduce you to the different classes of organic compounds. But before we do that, I want to show you some of the functional groups that we are going to encounter during the course of this semester. And I noticed that your book sort of uses functional group and classes of compound as if they are the same thing. There is slight difference, but for the purpose of your hour, consider them as the same. Okay. Now, on this slide, what I've given you here are some of the common functional groups that we will encounter in organic chemistry. Anytime you have an oxygen attached to an hydrogen, we call this an hydroxy group. Call it an hydroxy group. Anytime we have a carbon-oxygen double bond, this group right here, carbon-oxygen double bond, we call it a carbonyl group. So you are going to be hearing us using carbonyl, hydroxyl, and all that. Anytime you have a carbonyl attached to an hydrogen, we call this a formyl group or aldehydic group. Anytime you have a carbonyl attached to an hydroxy group, which is this group right here, notice this is carbonyl hydroxy group, then we call this a carboxyl group. Of course, we have the carbon-carbon triple bond. We have the carbon-carbon double bond. And then we also have what we call the alkoxy, which is also fairly common. The alkoxy is when you have an oxygen attached to a carbon atom. Okay. I should also let you know that for convenience, very often we use what we call the R group. For example, if I have this here, supposing I have this molecule. If I have this molecule here, Okay, what kind of functional group do I have here? That's a carbonyl group. Now, if I do not want to pay attention to this part of the molecule, right? I could simply just do this. And simply write R. In other words, R will represent just any group that we don't know of. It's just a group. Generally, there is carbon in that group. Okay, so the R is a generic a symbol that we use to represent most fragment that is not of interest in that particular context. Okay, so you see us use a R group very often. For example, I could tell you to give me a carbonyl attached to R group, in which case to be this here. So now, having said that, let us now go to the different classes of organic compounds. This you need to know. Those functional groups, you need to know them. That's pure memorization. These classes of organic compounds, you need to know, pure memorization. And I told you, your book simply refers to the classes of organic compounds as functional groups. Sometimes you say, give the functional groups. What your book is really saying is give the classes of organic compounds. So what do we have? Any molecule in which you have a carbon atom, notice we are using R here, attached to a carboxyl group, we call it a carboxylic acid. So that is a class of organic compound that is very important. Whenever you have a carbon-carbon double bond, that class of compound is called an alkane. Whenever you have a carbonyl attached to two carbon atoms, we're using R here to represent that we have carbon atoms here. That molecule is called a ketone. Whenever you have a carbonyl, it's attached to hydrogen, and that carbonyl is, for the most part, attached to carbon atom. That is called an aldehyde. So you need to recognize this. So if I have this, now what class of compound is that? What class of compound is that? That's an aldehyde. So this would be an aldehyde. Okay. Okay, supposing I have this. What class of compound is that? A carboxylic acid. Now we also have what we call the ester. In the ester, you notice the difference between the ester and the carboxylic acid is that instead of the hydrogen, we now have some kind of alkyl group attached to the oxygen. Okay? So we call that an ester. For example, supposing I have this molecule here. What class of compound is that? That is an ester. Of course, we also have the alcohol, in which you have an hydroxy group. In this case, the hydroxy group must be attached to an sp3 carbon. Okay, for example, if you have this, that would be an alcohol. That's an example of an alcohol. Now, supposing I also then go further to ask you, what type of alcohol is this? Primary, secondary, or tertiary alcohol? What will it be? Tertiary alcohol. And that is why it's important to know the different types of carbon. So this would be a tertiary alcohol. Supposing I tell you to draw me a primary alcohol, what will it look like? A primary alcohol. Will it be? Yes. Because the hydroxy group is attached to a tertiary carbon. Okay? So if I tell you to give me a primary alcohol, it would be this. In other words, the hydroxy group must be attached to a primary carbon. Okay, so this is a primary alcohol. So that is why the designation of primary, secondary, and tertiary carbon is very important. It's not time here. We've still got plenty of time. I don't know why you guys are moving. Okay, so now we also have what we call the ether. In the ether, you have oxygen is attached to 2 carbon atoms. We call that an ether. In which case, for example, this would be an example of an ether. In which you have oxygen attached to 2 carbon atoms. And finally, on this slide, you see here, we have the alkyl halide. In the alkyl halide, you simply have the X here stands for either fluorine, bromine, iodine. Those are what we call the halides. So in this case, an example of an alkyl halide could be this here. Okay, attached to a carbon atom. So these are all of the different classes of organic compounds. And we are almost finished with chapter 3, except the conformation. But I'm going to wait until we finish chapter 4 before I get to confirmation. So having said that, I want to introduce you to chapter 4, very briefly, 2 minutes of chapter 4. 2 minutes of chapter 4, because of the similarity between them. By the way, do not forget tomorrow we do have online review session tomorrow. Okay. Just let me give you 2 minutes of chapter 4. It's very important. Okay. You already know them. The cycloalkanes. Cycloalkanes are nothing, just as the name suggests, alkanes that are cyclic. Okay, for example, look at this here. Alkane with 3 carbon atoms, right? We call it cyclopropane. All you need to do is put the prefix cyclo in front of the name to get the name. This is a 3 carbon molecule called cyclopropane. 4 carbon cyclobutane, 5 carbon cyclopentane. If it is 6 carbon, what will you call it? Cyclohexane. Okay, so supposing I therefore have this. If I have this molecule here, what will you call that compound? No, bromocyclohexane. That would be bromocyclo. The same way you name the regular alkane, that is the same way you name the cycloalkane. Bromocyclohexane. Okay, so now I will see you guys tomorrow. Don't forget at 8 o'clock. I will remind you, and I will send you the link also. Do not forget to pick up. Do not forget to pick up your quiz, the one you took last Thursday.